Hello people, this is the second lecture. Today we discuss a case study of implementing the PageRank algorithm using MapReduce. The previous week we learned the basic of parallel computing using the MapReduce programming model. This week we will study how to use MapReduce to implement PageRank algorithm. It is a kind of graph processing algorithm employed by Google's search engine to measure the importance of web pages on the internet. According to Google's definition, PageRank estimates the importance of websites based on the number and quality of links to them. The rationale behind this algorithm is that more important websites are likely to receive more links from other websites. If we look at the algorithm from the mathematician's viewpoint, PageRank can be categorized as a probability distribution problem. In this slide, we can see a sample web graph showing PageRank values for a small universe of a few web pages. Each node in the graph represents a web page, and edges between nodes illustrate hyperlinks in the web pages. In this example, PageRanks are expressed as percentages. The higher rank value indicates greater importance of a particular web page. For instance, website C here with only one input link has a greater PageRank than page E with several input links. This is because the one link to C comes from an important page with a greater PageRank. This slide gives us more details about PageRank and briefly summarizes how it works. In mid-1990s, Larry Page and Sergey Brin introduced the PageRank problem. They considered two metrics to estimate the importance of a web page. Those metrics are the number and quality of pages that link to a website. They proposed an iterative algorithm to solve the problem. In this algorithm, all pages are given the same rank at the beginning. Then, in each iteration, each page gives an equal fraction of its current rank to all pages that the page links to. This is called the contribution of a node to the page rank of its outlink node. For instance, page Y in this web graph equally donates its current rank to all outlink pages A, B, and C. We will further study the algorithm later on, so don't worry about its details. Before going through the implementation phase, I want to present the PageRank formulation. Suppose we have a web graph consisting of n web pages or nodes. The PageRank of a given node U in the web graph is calculated based on this series. In this series, PR represent PageRank. In and out sets here determine in-link nodes to and out-link nodes from node U. For instance, this figure here shows a given node U. In U determines a set of three nodes A, B, and C linking to U. Similarly, out U is a set of 5 nodes D, E, F, G, and H. In this example, as shown here, the size or cardinality of in U and out U sets are 3 and 5 respectively. Here, we have an iterative serial algorithm calculating the page ranks of web pages or nodes in a web graph of n pages. At the initialization step, the algorithm sets the PageRank value of each node to 1 over n. So in the beginning, the PageRank of all websites is the same. The algorithm in each iteration updates the PageRanks of nodes based on the contributions of their neighbor nodes. So, to find an accurate estimation, the algorithm repeats the computation until the PageRanks become steady and doesn't change. As we can see here, the PageRank of each node is calculated using the series discussed in the previous slide. This slide details the algorithm explained in the previous slide. Okay, so far the serial PageRank algorithm was discussed. Now we want to study the MapReduce implementation of PageRank. First, we start with the map function, which is shown in this slide. The map function calculates the PageRank contribution of nodes to their neighbors. It takes an input file where each line in the file represents adjacency between nodes. For instance, we have here a sample node Y linked to 3 nodes A, B, and C. For this node, the input line is equal to Y 0.75, A, B, and C. Y is the node ID. 0.75 is its current PageRank. A, B, and C determines the outlink nodes for Y. The other input parameter is key that determines the line number in the input file, and we won't use this parameter in this code. Okay, let's scrutinize what the map function does. At first, we have function getOutLink. The function extracts the outlink nodes for the underprocessing node. If you look at our example, the underprocessing node here is Y, and its outbound links are A, B, and C. Then the PageRank contribution of the underprocessing node to its outbound nodes is calculated. The contribution is obtained by equally dividing the PageRank of a node among its all outlink nodes. In our example, the PageRank of Y, which is 0.75, is equally divided between A, B, and C. Therefore, 0.25 is the PageRank contribution of the node Y to its outlink neighbors. Finally, the for loop yields the contributions as a set of pairs, as shown here. After mapping, it comes to the reduce step. The reduce function gets all the contributions from a given node and aggregate them to calculate its PageRank. Remember that the shuffling step in the MapReduce programming model directs all the pairs with the same keys to same reducers. Consider a web graph including 10 nodes. So n in this example is equal to 10. We have here only 5 nodes of the sample web graph. The particular node A receives 2 PageRank contributions from X and Y. So the reducer receives 2 pairs A, 0.1 and A, 0.25 from the mappers. The reducer then aggregates these 2 values using the PageRank equation discussed in the slide number 6 and yields the PageRank for node A, which is equal to 0.31. This way we can obtain the PageRank of nodes using the MapReduce implementation. This slide summarizes the details of the map and reduce functions, which I have explained earlier. Now I want to ask you a question. Do you think it is enough to calculate the rank of each page only one time? Of course no. Since page ranks can fluctuate, we need to repeat the calculations several times and update page rank values in each iteration. In fact, one round is not enough to obtain accurate ranks. I explain this using an example in the following slides. Here we have a web graph including 5 web pages A, B, C, D, and E. Using this example, we will investigate how the PageRank values change during iterations. Based on the algorithm proposed in slide 7, the first step initializes the PageRank of all nodes to 0.2. During the next iteration, the algorithm calculates the PageRank of each node using the ranks obtained from iteration 0. In this slide, we can find how the PageRank for nodes A and B are calculated. The PageRanks for the rest of nodes can be obtained in the same manner. The table here summarizes the PageRank values per iteration. Similarly, the next iteration updates the page ranks of nodes using their current ranks obtained from iteration 1. In the table, we can see the differences between ranks calculated in iterations 1 and 2. So, this example practically shows that we should repeat the calculations until the page rank values become steady. As discussed in the example, PageRank values in each iteration are updated using the ranks obtained from the previous iterations. It means that we should execute our MapReduce algorithm for PageRank as many times as required to obtain the final ranks. However, there is a problem, and I would like to explain this problem by using an example. Here, we have the input and output values for one iteration of our MapReduce PageRank. As presented here, the input is a set of lines, where each line includes a node ID, its current rank, and its outlink node. However, on the other hand, we have the output file for the iteration, which is a set of lines. Each line includes a node ID and its rank. As discussed earlier, the output of each iteration should be used as an input to the next iteration. However, as we can see here, the output file of an iteration is not suitable that can be used as an input to the next iteration. In fact, there is no information about the outlink nodes in the output files. To address this problem, we should modify our MapReduce implementation so that the output of each iteration contains the outlinks of each node. Here, we can see the modified map function. First, the ID and outlinks of the under-processing node are extracted and emitted. Then, the mapper calculates and emits the contribution ranks. So, as we can see here, the map function, apart from the contribution ranks, emits the outlink nodes of the under-processing node Y. This way, the reducers will know the adjacency between nodes. This slide presents the modified reducer. This function uses the outlink lists produced by the mapper to include the outlinks of nodes in the output files. The if clause here is responsible for analyzing the outlink lists. In this example, in addition to the rank contribution of nodes X and Y, the reducer for node A receives a list of its outlink nodes, which are F and G. After calculating the new page rank for A, the reducer emits a pair consisting of the node ID A, its up-to-date rank, and its outlink nodes. This way, the output pairs returned by the reducers can be reused by mappers in the next iterations. You might ask how many times the algorithm must iterate. To answer, I should say that we stop when the page ranks become steady and converge. We didn't discuss convergence in our PageRank algorithm, but in practice, PageRank is run for some small and fixed number of iterations. You can find the details of the iterable map and reduce functions here. I have explained all in the previous slide. Please note that in Lab 2 and Lab 3, we will implement the PageRank algorithm using MapReduce in Python. Okay, that's all for today. Please let me know if you have any questions.